Hey everyone, this is my video on the solids of revolution, talking about something called cylindrical shells. And this is kind of a continuation off of our disk washer look at solids of revolution, but with a different method. So this method can come in quite handy when with disks or washers you might have to break up a region into several pieces, whereas with shells you might not. So um, it's not meant to replace discs or washers. It's just meant to be used in different contexts. So we'll talk about that a little bit later, but let's go ahead and just start with what is this idea of a cylindrical shell. So what we're going to do is draw a skinny rectangle parallel to this line, and then we're going to rotate it around the axis. So just like before, we kind of drew a skinny rectangle that was perpendicular for discs and washers. This time we're going to draw one that's parallel. So this is my rectangle that I'm looking at right there. And we're going to rotate that around this axis. So it would form something like this. Looks like a tube. And that tube is what we often call a cylindrical shell. So it looks like a cylinder, right? So that's kind of where that comes from. But it's hollow inside, right? So extremely hollow, basically just like taking a toilet paper tube or a paper towel tube, just that thin shell that's around it. So that's kind of where they get this name of cylindrical shells. And mathematicians are generally lazy, so we just shorten it to shells instead of having to write out cylindrical all the time. But what we want to do with this is find what is the volume of this cylindrical shell. And I don't mean the volume inside the whole cylinder, just what amount of space is taken up with just the thin outside edge of this object. So it has, a little bit of thickness, not much, just a tiny bit. And what is the volume of the actual object space? So like the cardboard that would take up the paper towel tube or the toilet paper roll tube on that guy. So the way you can think about it is if I cut this along this edge, so if I just kind of took my scissors, sliced along it, unwrapped it, what would it look like? So it'd look like this rectangle, and what we want to do is, remember this rectangle has, a tiny bit of thickness that's going to go down the edge, just whatever thickness of that tube is. Basically the thickness of the rectangle as you cut it and then unwrap it, got that little bit of thickness, and that will correspond to either a dy or dx depending on if this is a horizontal tube like I have here, or maybe a vertical one if I were rotating around a vertical axis. So in this case I'll just call that thickness a dy, or it could possibly be a dx if you're in a different scenario, oriented vertically. The length here is going to be whatever the length of that rectangle is. That'll be this guy right here. So we'll call that, I'm going to call this the height of my tube. I'll say that's my height. And then whatever radius I get here, right? We need the circumference of this guy right here. So I'm going to call that radius r. And then we need circumference. So in case you don't remember, circumference is 2 pi r for a circle. Basically the derivative of area. Area is pi r squared. Take the derivative, you get circumference, 2 pi r. So that will be this length right here. So 2 pi r. And you could call this width or height or whatever, but generally with these rectangles, if they're vertical, we'll think of it as a height, and I'll just keep that notation right here for this one. So the volume of this kind of thinnish rectangle is going to be 2 pi r times h, and then times whatever that thickness is, like dy, dx, whatever the case may be for these guys. So I'll just put or dx kind of over here in parentheses. And this is what we're going to do for pretty much any shell. So this is the volume of one particular shell. All right. Now you probably have a good idea of what's going to happen. We're going to add up a whole bunch of these shells with an integral and compute the volume that way. So that's kind of what we're going to be looking at on these guys. All right, so just real quick, the general formula, we just saw that up here, 2 pi r times h, and then that dy or dx. If I added all these up, what would I get? So again, that's going to be my integral from some a to some point b of this 2 pi r times h times that, again, dx or dy on those guys. So you'll just be looking at, in this case, where do my rectangles run vertically, height A to height B, or if they're up and down, left to right, A to B on those. And then how would you describe the difference between a washer and a cylindrical shell? So this is kind of your own personal look at it, just thinking about what the shapes look like. For me, the washers are definitely more flat. They take up very little space in one of the dimensions, whereas shells generally take up a lot of space in all dimensions if you think about how they're placed. But there's just little volume because a lot of it is hollow space in the middle for those guys. So unlike washers, which are basically 2D objects, these are 3D objects as they get rotated around the axis. They're just really thin. So you can think of it as just stacking a bunch of these thin pieces together to form your object. All right, let's go ahead and go on to an example, look at calculating one of these out. So we've seen a similar shape to this before, but this will just show you how this goes in rather than a washer setting, in a shell setting. So I have this function, y is this negative x minus 3 squared plus 4. All right, so we're going to take a look at this familiar shape. We did this with discs and washers. We're going to try it with shells this time. And there's my function, y is negative x minus 3 squared plus 4. And again, I'm going to ask myself, what is the axis of rotation? And in this case, just like before, it's kind of right down the middle of this object. And that will correspond with the y-axis over here. So you can either write in y-axis or the equation form, x equals 0. Darken in the axis, draw a sample rectangle to rotate. So this time, again with shells, I'm going to take a rectangle that's looks like this vertical, parallel to my axis of rotation, and I'll go ahead and rotate that around. So if we rotate that around, that'll look something like that. And I'm looking at what is the volume of that general sample shell. So remember, that's going to be my 2 pi times r times h. In this case, our thickness is just a small change in x, so dx for this one. So really it comes down to what is the r, what is the h for this guy. And the height is usually the easiest for most students, so we'll go and start with that. So I got this point that's right up here, this other point that's down here. We're just trying to find out how far that is. So that is my h. And if you think about it, it's whatever this y is on top minus whatever that y is on bottom. So we'll go ahead and come down here and say h is that y1 minus y2. And for us, that's going to be the y on top is just that parabola. The y on bottom is 0. So in this case, that's just going to be that negative parenthesis x minus 3 squared plus 4, and then minus 0. So nothing happens with that. The r, this one can sometimes be not the hardest, but maybe the most confusing for a lot of students. So how far is it from my y-axis to this point right here? And again, we'll think of this as, say, just some point xy on here. I go over a distance x, I go up a distance y, and that's what I get. So this I could just call a distance x, right? I'm going from my y-axis over this point. That distance is x. From my x-axis up, it's a distance y, but we want things in terms of x because I'm using this dx. But notice with the r, I don't have to change anything. I'm just going over a distance x. I want it in terms of x. It already is. So we'll just say r equals x. And that's it. So there's my value that I'm going to use for r. Here's my h. And then we just got to put it all together. So again, a lot of times your r is going to be not that complicated of a thing. It's just going to be x, or if the axis of rotation is somewhere else, maybe like a x plus 2 or a 2 minus x, or just kind of varies. We'll do some of those later on. All right, so go ahead and set up an integral and then approximate it. So this part is usually the easy part once you get this far. So we're going to do an integral of 2 pi times our r, which is x, times our h, which is this negative x minus 3 squared plus 4, and then our dx. And our x's are going to run from, looks like 1 to 5. So those x's will go from 1 up to 5. And go and calculate that out, see what you get there. So I get 201.062. Again, you can use this on your calculator or Desmos just to calculate that value. And this should match with the other one that we got with washers. Washers was a little harder because you had to rearrange the equation and do all that stuff, but shells works pretty nicely with this one.